Dear students, welcome to Module 6, which is on 3D electrodes and current distribution. The learning goals of this module are the following. You should be able to explain why 3D electrodes are used in electrochemical applications and what their requirements are. You should be able to make calculations on porous electrodes and separators based on tortuosity, porosity, and interfacial area. And you should be able to qualitatively predict primary, secondary, and tertiary current distribution for an electrochemical reactor. Let's start with the first part of this module, which is on 3D electrodes. 3D electrodes. Actually, we don't see them so often in an electrochemical laboratory. There we see electrodes like this one, with this plate, for example, this platinum plate at the end. We call that a flag electrode, or this rotating disc electrode. Really 2D electrodes. And also for industrial processes, we often depict them as plates, which you can see here. So we have here an electrode, then we have the electrolyte, then the separator, then the electrolyte, and then another electrode. But in practice, these processes typically don't use these flat plate electrodes. Instead, they use 3D electrodes, of which different types exist. Mesh electrodes, porous electrodes, and gas diffusion electrodes. And we will now explain them one by one. Let's start with the mesh electrodes. Mesh electrodes are basically still mainly 2D, but the difference is that they have holes. You can see an example here of a perforated plate electrode, and you see all these black spots are basically the holes, and the gray stuff is still the metal structure. So there's a lot of open space. Now, why are these electrodes interesting? The main reason is that you can use them to make a so-called zero gap configuration. Now, what is a zero gap configuration? For that, we can look at these two pictures. Here we see basically the same picture as we saw on the previous slide. We call that a finite gap configuration. And here we have a configuration which is called a zero gap. Now, what do you see? You basically see here all these things. And that is the electrode. Those are these metal parts which are pressed against the separator or membrane. And the same applies on the other side. Now, why is that attractive? In this way, you bring your electrodes very close to each other. There's only the membrane in between, and you don't have the ohmic resistance of the solution. So you minimize that ohmic resistance. Also, you minimize the effect of possible bubble formation. As you can see here, lots of bubbles. And the bubbles in this, there's still bubbles here, but the bubbles are not between the electrodes. They are on the other side of the electrode, and then they don't add to the ohmic resistance. And thirdly, the zero gap configuration also gives extra support to the membrane. Here the membrane is very loose and it can basically move in all kinds of directions, which can lead to tears or can lead to less efficient operation. But in this configuration, you basically sandwich the membrane between the electrodes and you give it a lot of support, keeping it nicely in place. So this is why this zero gap configuration is quite attractive. It typically results in more energy efficient electrolysis than the finite gap configuration, this one. And therefore it's used, amongst others, in chloralkali electrolysis, but also in water electrolysis. Now, what are typical requirements and materials used for mesh electrodes? Now, the requirements are listed here. The material should enable good liquid transport through the electrodes, because the reactants should still be able to reach the electrode material and also reach the membrane. So there should be good liquid transport. Then the material should allow for a good gas removal. We want to avoid that any bubbles are trapped between the electrode and the membrane, because then they give a lot of extra resistance. Thirdly, the electrode should have sufficient mechanical strength. We don't want it to easily bend or so. So this is important. And the last one is basically a general one related to electrokinetics. We just want to have a very high surface area of the electroactive material. This we can do at the nanoscale, but we can also do it at the micro scale. As you see here, if you, for example, use a woven meshes, yeah, that brings quite a lot of electrode area, and this especially applies to metal felt, where you see a very high electrode area. So that is attractive. On the other hand, for metal felts, you could worry a bit about gas removal, because if a bubble is stuck here in the wrong place, it's probably not so easy to get it through this felt to the other side. And this, yeah, basically also brings me to the different materials that you can use: meshes, perforated plates, expanded metal meshes, or this metal felt. And it really depends on the application. For example, if you have gas generation or not, or how important your liquid transport to the electrode is, what is the preferred material. So it's really application dependent. Let's move to the second class of materials, namely the porous electrodes. These porous electrodes are really 3D structures, and they are used in applications where the electrode area is really important. And a nice example is the battery. In a battery, you basically want all your material to be able to react, because you want to transport from the anode to the cathode, and you want basically all the anode material and all the cathode material to be able to react, because in this way you can store the most energy into the system. And this means that basically all the material should be exposed to the electrolyte, and this is why you want to have a highly porous material. But it should also not be extremely thin. It should not be a 2D material, because then you hardly have any capacity of that material. Let's quickly look at an example of the use of porous electrodes in batteries. Here you see a lithium-ion battery, and you can see that it has an anode layer and a cathode layer separated by the membrane. And you see, yeah, what these porous structures that exist on a relatively small scale. So these layers are only 65 micron for the anode and 75 micron for the cathode, lithium cobalt oxide. And you see how porous these materials are, just to be able to give access to the electrolyte to all the material. There's quite some complexity in these porous electrode materials that are used in batteries. You should keep two important things in mind. A battery is either charging or discharging, or standing still. But in this charging and discharging process, we are basically never in a steady state, because materials are going from their oxidized to their reduced state, or vice versa. And once they have reached that state, they cannot react further until the battery is put in reverse mode. So that adds a certain time-dependent complexity to these batteries. At the same time, we also have to think that materials that are close to the electrode will react faster than materials that are further away from the electrode. This is also important to keep in mind. So we have this time-dependent complexity and also this location-dependent complexity. Now, to reduce the influence of the latter, you typically see that battery materials are quite thin. We saw it on the previous slide, only up to 100 micrometer. And that is because if you make them thicker, you really get a large influence of this location. So I would recommend you here to answer quiz question 6.1 before we move to the next type of electrodes. Let's move towards the last type of 3D electrodes, namely the gas diffusion electrodes or GDEs. Now, these are used for the reaction of gases. Now, why are these 3D electrodes used for gases? Now, let's have a look here at this example of CO2 electroreduction. Here you see a classic electrochemical system. If you want to react the CO2 here, you first dissolve it into the medium, then it moves towards the electrode and reacts to CO. Now, the issue is that the solubility of CO2, basically of any gas, in a liquid is relatively low. But you still need the liquid in the electrochemical system because of the conductivity. As a result, you quickly run into mass transfer limitations. You reach the limiting current as we discussed in the module on mass transfer. Now, in a gas diffusion, you do something like this. You still have the liquid, but now you flow the gas from the other side through the porous material. And what's now the advantage? Here you have a gas phase, and the fusion rates of gases in a gas phase are much higher than through the liquid phase. And here only there's a small layer of liquid, but this layer is only relatively small, and therefore you can reach a much higher limiting current density with this system than with that system. And that's why these gas diffusion electrodes are used in, amongst others, fuel cells, but you can also use them for CO2 electroreduction. Let's look a bit more into detail into a gas diffusion electrode. It consists of three layers. On top is the catalyst layer, where the reaction actually takes place. This layer is basically in the liquid, so also has contact with the electrolyte. The second layer is the microporous layer. In this layer basically blocks the liquid from going to the other side. But it still allows the transport of the gas. The third layer is a certain substrate layer, and this provides a certain structure, so keeps the electrodes in place, and also provides electronic pathways, so the electrons going from the catalyst material can go through this layer and then later to the backplate of the electrode. One big challenge with GDEs is flooding. That is depicted here. Here you see the liquid with the catalyst layer and the other layer, and in principle this layer should block the liquid, but it's not always successful. And especially over time, flooding can start to occur. And basically what then happens is that liquid moves through this layer to a place where you don't want it, namely in the back. And there it can cause all kinds of problems. So you would like to avoid that. So you really need to design your gas diffusion electrode very well to avoid that. And this concludes this screencast on the different types of 3D electrodes. Thank you for your attention.